Welcome everybody to the last lecture. Since Tuesday morning isn't a regularly scheduled class, we are not going to introduce new material because I have no ability to impart it to the Tuesday section. And so we're going to have a little bit of a chance to talk about something that is a little different, which is more on network security. So you'll remember last time, just to kind of recap for you guys, one of the last things we talked about was public key encryption. And public key encryption is where you have two users, Alice and Bob, and it finally, after all these years, occurred to me last week that they chose them because it's A and B. So I'll show you something else that blew my students' minds in Mexico because maybe I always think I'm like the last one to figure stuff out, but on the Mac calculator, it has a programming visualization, and you can click bits in the binary piece of it, and it will tell you what the number is in decimal. Or you can type the number in decimal, and it will show it to you in binary. Did you know this? Yeah, so I got to remember to pick up my extra calculators now that you mention it, because I shamed the department into ordering a few more for exams, so we can kind of learn them out. I've owned a Mac since the day one. I literally was the very first human being in line to buy a Mac on the very first day they went on sale at universities. They were not sold to the public. They were sold to the university, and I had the signatures of the engineers in the case inside my original Mac. And then at one point, the power supply was recalled, and I took it to the place up in Spring because there weren't Mac stores everywhere, and they gave it back to me and said, hey, you got a new case out of it as well. And I'm like, what? And they go, yeah, the warranty also included the case because it had melted a lot of people's cases. Yours looked fine, though. And I'm like, okay, so where is it? Well, we threw it out. Yeah, so they threw out a case that had the signatures of Steve Wozniak and Steve Jobs, and you know, what popped through my mind was Racehorse Haynes, who was a very famous lawyer. He was Dick DeGuerin's protege. Dick DeGuerin's the guy that represented the Branch Davidians and the lady that killed Selena and a bunch of others. He's like a high-flying criminal defense attorney. His mentor was this guy called Racehorse Haynes, who literally had a shingle hanging out with his name on it on a little thing that's swinging outside his door. He's the guy that got a law passed in Texas called justifiable homicide, based on the theory that some folks just need killing. And he got every murderer, a person accused of murder in his entire career ever defended off except one guy, and he got that guy a retrial because he said he was sick and didn't really give it his best, and he just didn't feel like giving the guy great defense because he shot his wife while she was on the toilet. So even when he lost, he still managed to get the guy like another trial. Never lost a case, his whole, can you believe that? So when this guy told me he threw away my Mac case with the signatures, I'm thinking like, I could probably get off if I killed him right now. This is probably justifiable homicide. But how long would it take to explain a jury, like, you know, no, it's like these are the really famous people, and like nerds will not win this one. So I just said, okay, well, that's gone, so it's over now. So you know, I hope he did. I hope he wasn't so stupid that he just didn't throw it away. Maybe somebody will find it, you know. Maybe it'll be like that singing frog. Hello, my honey. Hello, my, you know. All right, so with public key encryption, we had, just to recap, because you're going to need to know this. Okay. So Alice has a public key, and Bob has a public key, and Alice has a private key, and Bob has a private key. So do you remember the problem that RSNA were Rivas, Shamir, and Edelman were trying to solve by coming up with this double key system? What the key problem was that with every other password scheme we had ever come up with, you couldn't use the communication channel to send the password because the communication channel was what you needed the password to secure. So you always had to have two ways of doing it. So I told the story about the FCC when I was a volunteer at Rice's student radio station. the SEC would mail us this big orange folder every month, and it would have a little envelope inside of it that had a couple of keywords like Bravo, Delta, and if you had to have a radio there, and alerts would come over the radio from the National Weather Service or flooding or things like that. But if the president needed to make an announcement to the entire country, these things would go off and they would tell you basically patch the radio into your broadcast. So in other words, let someone take over the radio station. So before you did that, they needed a little safeguard. So they would read out audibly this 2-word password, and you would look inside and make sure that it matched the one that was in the card. And if it did, like, Delta Bravo or whatever, then you would, connect the two together, and it would give you probably a full minute's head start to flee the city before everybody else did. Because there's only one reason on the planet that the president was ever going to do that, and that's if the Russians had hit the button and the missiles were on the way. So it would be like a goodbye. It would be a different type of fireside chat. Okay. So anyway, that was a perfect example of how they had to mail the passwords because they could not send them over the radio network that they needed to secure. And most passwords work this way. If you get something that says, type in the code we just texted you a code on your phone, please type that in so we can let you into the bank, or Microsoft's Authenticator, or any of these other kinds of systems. I used to have one-time passwords that were on a sheet, and every time I used one, I'd run a line through it, but they had to mail that to me because they couldn't obviously email it over the network they were trying to secure. So this is a huge issue, and it limited people's ability to implement encryption and to secure communications messages, because who wants to have to get something in the mail from Google before you can connect to their webpage to do a search every single time? It just didn't make sense. So these guys came up with a scheme that revolutionized the way we use security and encryption, and it's called public key encryption. And it's based on Euler's formula, a couple of 100-digit plus long prime numbers, and what's a class of math algorithm. It's called one-way trapdoor, which means it's very easy to calculate an output based on an input. You take the input, you put it through your algorithm with a key, you get an output, but it's almost impossible. In fact, we're counting on it that it is impossible in any reasonable amount of time to go backwards. That if I give you the output, you can never figure out what the input was. Even if I give you half the key, you still can't figure it out. So that was the basis for public key encryption. And so what public key encryption does is, if I have a message, M, that I want to send to you, if I encode it with my private key and I send it across this medium, I no longer have to worry about who can see it, because everyone can be assured that it really came from me, because when I take the message at the other end and I run it through the algorithm, but this time with my public key, which anyone can get, they're going to get back the original message. So anybody that sees this can be confident it came from me. No one else could have possibly authored this message, because if my public key decrypted it, my private key must have encrypted it. And I keep that key private. So I never have to send any secret thing to anyone else. The public key that you need is just that, public. I can publish it and anyone can get to it. The problem with that is, what if I only wanted, Bob to read it? Everyone can read it. Anyone can decrypt this message. All they know is that they can be absolutely certain it came from me. So what if we do it backwards? What if we do it the other way around? What if instead I take the message and I encrypt it with Bob's public key? I have access to that. Bob publishes it. It's available to anyone. And one of the interesting things about this algorithm is, if you do that, Bob can decrypt it with his private key. Whoops. And you will get the same message back again. So now anyone can encrypt the message with Bob's public key and send it to him, confident that only Bob can decipher it. No one else will ever be able to make heads or tails out of it. So it's very safe for me to send Bob a message. Anyone can intercept the message. They can see it along the way. I'm increasingly getting the idea to not talk to you about this on last lecture. And so this thing will decrypt it. So by combining the two together, you've got magic. So when you combine the two together, what you basically do is take a message. You're going to take this thing here and feed it as your input here is basically what's going on. So I'm going to take a message. First, I'm going to encrypt it with my private key. Then I'm going to take the output of that and encrypt it with Bob's public key. And I'm going to get some sort of a doubly encrypted message. It's like double secret probation on Animal House, if you guys ever watched that. And if you didn't, I'm flunking you. Okay, so here's how you would decrypt it back. Anybody want to guess what we do on the other end? What key do we use? Yeah, A, public, and B, private. And you will get the message back. This time, I can be certain that only Alice could have sent it, only Bob can receive it, and anyone can see the message on the network, and it won't do them any good at all. So this prevents ever having to send anything that must be kept secret over the network or over any other type of channel. It's genius. It revolutionized things. And RSNA became very famous, household words. There's a company, RSA Security, and they became wealthy. There are 2 universities on Earth that have generated more spin-off companies than maybe all others combined. I doubt it, but certainly way more than anyone else. And it's Stanford and MIT. They've each generated about 22,000 companies. And Stanford keeps track of it. Every day, 3 million people go to work, and it generates $500 million in whatever a month. So they keep track of those kind of statistics. Good luck catching up to those guys. But 20 years after these guys became famous and rich and had a bunch of conferences based just on this, lots of products, etc., the people that discovered it first for the British version of the CIA, M5, finally had their work declassified, and they were able to publish the papers proving that they had done it before RSNA. So I had a boss once that said, you can either have fame or fortune, but you can't have both. You must pick one. I'm like, okay, I'll pick fortune or fame or whatever it was at the time. I don't remember what I told him. Okay, so that's one of the key ideas. So mathematically, we have to be sure that these keys are big enough that they cannot be decoded or they're not subject to what's called a brute force attack. So what a brute force attack does is it just tries every possible key to see if one just happens to generate something that looks like, I don't know, English or an Excel spreadsheet or whatever it is you think was being transmitted. And if you can stumble across it, then great, you're in. So on Stack Exchange, I don't know if you guys have ever been on that website before, but there's a whole bunch of sub areas of it. But it's actually incredibly interesting, and it's one of these sites where people vote down your idiotic answers and responses, and you get booted off the island pretty quickly. So you can have a lot of confidence that the information that's there, unlike every other discussion board you've ever seen in your life, actually has people that know what they're talking about. The idiots are thrown off. And people are really harsh. If you just like randomly pick some Stack Exchange page, it's a lot of fun to read it. Like, apparently you don't know how to read, because this guideline clearly says that this topic is supposed to be blah, 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 blah. I've shut down your post, I've moved it to the other forum, and I've taken 10 points off your reputation. And by my calculation, see you later, you're not going to be able to post again for a while. I mean, people are just like ruthless. So I'm scared to post. I'm scared to post. But the stuff is usually very informative and accurate. So one of the things this guy posted in this particular post was in response to people's musings over how do you have any confidence that your encryption algorithm is halfway decent. So this thing goes on for a while, right? So, and these people have 5,200 points, 33,000 points. I have, I think, 6 maybe, because I just don't try to post stuff here. So it goes on and on. But one of the things that came out of this was this guy posted a Google Sheet spreadsheet. And oh, here you can see here. Your math is completely wrong. Yeah, why not break the 128 bits, blah, 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 blah. This is post number 1337. You've confused P with P space. Some of these are nicer than others, basically ways of telling people they're idiots. Some smart people can. I don't know how you can say concretely, blah, 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 blah. The mobsters are brute, so brute force. Oh, so funny. Okay, so nerd humor too. It's like, but here's the spreadsheet the guy produced. And it basically says if electricity costs $12 a kilowatt hour and a server uses 427 watts and therefore 3,740 kilowatt hours per year, and you're going to spend $449 on the server, and it can do 1 times 10 to the 14th decryptions per second, and therefore this many per year, how many machines and at what cost would it take to break a code brute force that was 73 bits long? 2 computers and $1,000. Okay, we should probably not use a 73-bit key. How long would it take to do one that's 83 bits? 2,200 machines and $1 million. So a company might, go after something like that. 93 bits would be a couple of million machines and $1 billion. That would be like the Russians. Or 102 bits, 2 billion machines and $1 trillion. That would be like China or the United States. So, of course, you could throw this many computers at this problem and solve it in 2 minutes or something like that. So why don't we use 500-bit keys all the time? I mean, if more is better, why don't we use 1,000-bit keys for our credit card and the little VeriSign card reader machine at the Target checkout stand or at the gas pump? Why not use them? Why not use 1,000-bit keys or 500-bit keys? Too much means what, though? Which ultimately boils down to time. It takes too long to calculate and pass through the long key and figure out if it's the real credit card. You're talking about minutes or hours waiting for your transaction to go through. Nobody was willing to do it. So there's a business balance to all of this. Money, politics, and religion, right? So you don't want to slow people down. In fact, the CEO of Target and the CIO lost their jobs. The CIO was my customer when they had to disclose that for over a year, their point-of-sale card reader machines had all been infiltrated with code that had just captured everyone's credit card numbers for a year and a half. And the reason why they got fired over it was because they had had an option at the beginning of that time period to upgrade to chip reader card readers instead of just the mag stripe ones. And they tested it out, and it made its way up to the board. It made its way up to the CEO. And it took, 8 more seconds or something like that per transaction. And they said, no, that's too much. So for 8 seconds wait time, you had your financial data stolen. And it cost the credit card manufacturers. How many people in 18 months go to Target and use credit cards? They had to crank out another, 50 million credit cards and send them with the postage. And so I'm sure they sued Target over it, but it cost the CEO his job, and it should. So security is an area that it's very hard to break if you implement algorithms correctly, but it's also very, very brittle. If you leave some part of your security constellation out, you will fail. And so there's a guy named Dan Bonnet who is a professor at Stanford, and no, spell it right, it will help. And he's a very, very good lecturer. He's my favorite one I've ever taken this type of stuff from. And I paid for a bunch of classes, but there's a free one of them. They moved over and made it free. I think it's the same recordings as the ones that he gave when I took it. But, and I'm sorry, it's partly in Spanish because Coursera thinks I'm a Spanish speaker. I am, but sorry about that. So this class is free to join. It starts up in a couple of weeks. And the thing I like about Dan Bonnet is he has lots of horror stories about things that actually happened. And he'll call people stupid. It's a little bit like reading Stack Exchange. And so he'll talk about huge companies, including people that are in the security business, like VeriSign, that lost all of their certificates when they lost their master private key. And so it's interesting to kind of hear what goes on. His courses are in this particular institute's certificate program is not intended to teach you how to do security. It's intended to teach you what to look for in a security vendor so you know whether they know what they're talking about or not, whether they're bringing you a full solution or not, so you can help advise your management whether these guys are enough. You know, can they get the job done? Are they talking about the right kind of things? All right, so I wanted to switch mainly for today and share with you guys a talk that actually was written for U of H first, but the only PowerPoint I'm able to find is the version of it that I converted for Tecnológico. So I wanted to spend some time today, this is all fun, talking about DDoS attacks. Do you guys know what DDoS attacks are? Anybody know what it stands for?
Distributed denial of service.
Yeah, distributed denial of service, or just DOS attacks is also okay. But basically the idea behind a DDoS attack is you overwhelm someone to the point where they cannot handle the load. And the idea is by doing so, you prevent the legitimate users from gaining the normal types of resources and response times that they've come to expect. So I'll give you a real example that happened at the University of Houston in 1969. This was during the era when the civil rights laws had been passed in the United States, but black people were still not allowed in many restaurants in Houston. Not because the owner hated black people, but because he was worried about his place getting burned down. Because there were a lot of activists that, you know, Ku Klux Klan and things like that. I mean, guys, this may seem like foreign language to you, but, you know, when I was at Rice, which was in the 80s, there were old yearbooks in our dormitory college, and they had pictures where the Ku Klux Klan Club had a page in the yearbook. I mean, it's not long ago. It's just under the surface. So what a group of people did, including a really good friend of mine, they got a bunch of students together and they went to one of these restaurants around lunchtime, kind of early on for lunchtime, and somebody's unmuted themselves, so let me mute them, help them out here a little bit. Oh, no, they didn't. Must be my system making some noise. And they just occupied all the seats in the restaurant and ordered, you know, a glass of water and glanced through the menus and basically took up the whole restaurant and ordered nothing. The manager figures it out pretty quick, right? It's a denial of service attack. So none of the other people who were wanting to come in and pay for lunch could get in that day. So their point basically was, there's more than one way to shut down your restaurant. And we can be here every single day for the next year, and you'll go out of business that way without anybody ever breaking a piece of glass or doing anything like that. So which way do you want to go out of business? Do you want to go out of business for being a racist and not being brave, or do you want to go out of business because you stood up and, you know, the police need to help you? Or so this went on to try and force these businesses to change their practices. So that's a good example of a denial of service attack. Another might be if we all went over to McDonald's and we all got in line and didn't really order anything. So that's kind of the idea behind these types of computer attacks. It's just the only place I've ever given this talk where I actually know of a real example that actually happened at this place. So, and you'll be glad to know that my friend ended up in a position of setting security policy and things like that for Houston ISD. So we had a good guy in there doing that stuff. Okay, so they've been around for a long time. The first one was a direct attack, and we'll talk about what that means, but they've they've been migrating very aggressively in the last few years away from attacking network applications and the network itself to attacking programs running on servers. And there's a third class we'll talk about a little bit as well, and we'll sort of get a chance to understand who is it that's doing this. So the basic idea is that you can load software on someone's computer and then get that software to do something. So the way a lot of this malware works, if it's going to be used for a DDoS attack, is it will be loaded and it will sit quietly. It's either been told a day and a time when to wake up and reach out across the network to get the information on who they're supposed to attack. It's like a sleeper cell. Or you can tell it who to attack right up front, but it's going to sit quietly on that computer, and at that day and time, it's going to wake up and it'll be discovered when it does this, but it'll take some time. So it'll be able to, you know, send what could be perfectly legitimate looking requests to a server, but it'll do it in such a volume that the server can't possibly sustain it and will collapse. Right? So that's the idea. So viruses are ones where you catch it yourself, like failing to cover your mouth. Worms will work their way around taking advantage of known vulnerabilities. So the big attack on one of these providers in the last 18 months took advantage of a known bug in the version of Linux that was running on Android, on Raspberry devices that the owners never bothered patching. Well, who sits around patching Android devices and patching Raspberry Pis and patching, especially these little IoT devices like the ones that we played with? Yeah, you've got an IT department that worries about PCs, but who's worrying about all of these things? And so that's a big security risk as well. So 100,000 of them were infected and then brought down a DNS service provider for the better part of the day and a third of the internet. So there's lots of things that have been going on. One of the things I'll show you guys is cybercrime as a service, believe it or not. And there have been lots of app layer attacks replacing a lot of the ones for the network. So partly I'm relieved because they're getting the hell off of my gear and onto the apps, but I have to feign like I care. Like, oh, I'm so sorry, how can I help? At least it's not my stuff. So what's exactly being attacked? Everything at every layer imaginable. And so this slide's here for people that don't know what the stacks are, but there are lists that the United States government publishes of known attacks for tons of programs at every single one of those layers. And I'll show you a list of some of them. Generally, they fall into 3 categories. The last one is new and most alarming, ones that attack the hardware. Back in the, 90s, there was a very famous problem, and I bet I can find it. There it is. Just have to type in the name of the assembly language instruction, the floating point division bug. So in 1994, Dr. Knightley from Lynchburg College discovered an error in an early alpha version of an upcoming Intel Pentium chip that caused it to produce the wrong result, given a pair of floating point numbers. And he let Intel know, and they laughed it off and continued to ship the chip. It would have been the time to have stopped it. And if you think about the business of putting chips in things, the chip might sell for $50, but it goes in a $10,000 device. And there's no way to replace it like you would a bad radiator or an airbag or a tire. You're going to have to buy the whole computer back. So your exposure is an order of magnitude greater, or 2, if you're really unlucky, than the cost of the component that you supplied. So you may have to buy somebody a new computer because your $30 chip has a problem. So this was a huge issue for Intel. There was a big process error that caused this to happen because they didn't listen, and they ended up on the front page of every paper in the world. And this is like turning on the television in the morning and seeing escape routes out of the city. Usually not a good sign for the day. So let me see if I can find. Did you really? Did you take it to the guy in spring and he threw it out? How fun. No kidding. That's awesome. So what did they do? Wow. Yeah, that turns out not to be all that hard to do because of rounding errors, but yeah, so they had a big disaster on their hands. So that stuff led to a variety of solutions, one of which is to put firmware on your computer, which is a chip that can be overwritten periodically. On day 1 or 2, we looked at one of those little chips, and you can kind of rewrite code by going to the compiler manufacturers and telling them, don't hand me any assembly language instructions that use that instruction. Figure out a way to do floating point division like we learned in the computer architecture class using shifts and adds and stuff like that. It'll slow your computer down, and you write the person a check to say $250 off your next HP computer. So that's one of the things they did. Or you can rewrite the firmware on your code and do a firmware update. Make sure you don't kind of avoid that particular trap. If the number's between this and this and the other one's between this and this, then do it this way instead. The problem with having EEPROMs and reprogrammable control code on your system is people can change the way the computer works. And so one of the more recent attacks that's very alarming, like I said, is one that goes in and basically overwrites your BIOS, overwrites the firmware, and bricks your computer. It's completely unrecoverable. The only option is to throw it into recycling and buy another computer. So that one's really damaging, and so we got on top of that one really quickly, but that's a kind of a new area that's a little bit frightening. Lots of effective DDoS attacks use an approach called amplification. So if you are an attacker, if you don't want to get caught, you're going to probably want to use someone else's computer to launch the attack, and they may not have a fast enough internet connection to really ever do any kind of damage to someone, even if you find a bunch of them. So an amplification attack is one where you send a request, let's say, the response for which will be much greater in size than the request is, but you trick the person responding into thinking that the request came from somewhere else, and the somewhere else would be the subject of your attack. So I used to do this in college all the time. If people irritated me, we would call in pizzas for them, and the guy would show up with a pizza delivery, and they're like, I didn't deliver a pizza. Or we'd sign them up. We would go through the library, and you know those little free subscription cards we'll bill you later that are in every single magazine? We would just fill those out, you know, and they would just start getting like tons of magazines. So it would be a denial of service attack on their mailbox. So we, you know, nerds have ways of getting back. You can make fun of us, but you know what? We're going to win, and we have. So anyway, so that was an example of an attack like that. But those were amplification attacks. I could send one little piece of paper off, and they could get thousands and thousands of pieces of paper back over the next 6 months disguised as magazines, for example. So amplification attacks are used to kind of overwhelm systems even when you don't have enough bandwidth to do it yourself. So what software is vulnerable? Here's a list of just the protocols in UDP that make it onto the Computer Emergency Response Team website, which has been run for the longest time out of Purdue University, but it's basically quasi-government now. Let me pull it up and see if we can. I haven't pulled this up in a little while, so I'm hoping the web page is still there. Yeah, Cyber Infrastructure and Homeland Security. Here's a list of attacks for this. Quote of the day. Anybody ever heard of that one? Anybody heard of the Quote of the Day protocol? Believe it or not, it was an early internet protocol back when things were still fun and before we turned everything into super serious business. So here's a quote of the day example. Quote of the day. Let's see if we can find some in here. Check the presence of quote of the day. No, I don't want to do that. So it did exactly what you might think. You ran this protocol, you could send it out, and it would send you back an interesting quote, like, never do today what you can do tomorrow, or nobody lies on the internet, or the cake is a lie, for example. All right, so that's an example of one that somebody figured out how to hack, so they could send a request and start quotes flooding back, filling up somebody's network connection, for example. How amplified can it get? Well, just go to the very last row. The memcached attack is the way that attackers brought down, I want to say, almost a year ago to the day, GitHub. And GitHub is a site that has public domain software that you can use to get open source stuff. And apparently they ticked somebody off, probably for one of those quotes that I showed you earlier on Stack Exchange, like, you don't know how to do math apparently. And they're like, I'll show you. And so they got all these systems to send requests to web caching servers. Do you remember the web caching servers that we learned about? They'll keep copies of objects from web pages. And so when you actually have to go get a web page, maybe some of the content can come from a server that's nearby, that's local to you. And it can reduce network congestion and speed up the time it takes to get your page up, etc. So normally, the standard Windows-based web cache servers, they should be configured to respond to requests coming in from inside your network. But by default, they're configured to respond to requests coming from anywhere, including coming in from over the internet. Why would I have a connection to U of H's web caching server from China to ask it to help me load a web page? But that's exactly what happened. And so these guys figured out that if they send a couple of requests to a web caching server, the first time the page will, get loaded into the web caching server, so it'll make a copy of it, and now it has the copy. Once it's there, now you can send it like 100 requests saying, Bob would like this web page. And like, oh, I can help with that. I have all those things. Here, Bob, here, have 1,000 objects. So the New York Times web page is one where, how big is the packet? GET space index.html, next line, host : space nytimes.com. If you just send that, then you'll get back hundreds of megabytes worth of data, because the New York Times front page is like miles long and has hundreds of objects, and it takes dozens of TCP connections. So if I can just send that little snippet and cause all of that garbage to go flying, or maybe it's like a Windows 10 free download of a patch that's like a gig in size, whatever it is, you're going to get a huge amplification factor. So just go and ask 10,000 of these servers whose managers failed to configure them properly, and they will therefore take requests from the outside world and disguise who you are as who you are trying to attack, and they will think that's where the request is coming from, and they will send all the data back to them. So direct attack will get you arrested. A botnet attack basically infiltrates these systems, but an amplification attack disguises that it's coming from the target. And it's a perfectly legitimate request. You're not hacking into anything. You're not corrupting anything. You haven't broken anybody's code. You didn't have to install malware. You made a perfectly normal request. Hey, I'm Bob, and I would like a copy of the New York Times webpage. And its job is to answer that and send it to you. Just like the magazine's job is to mail my friend a copy of Southern Living, even though, he's on the football team. So, and there's a lot worse magazines you can request. We got to the point where they wouldn't deliver pizza to our building, so that kind of backfired. Nobody could get pizza anymore. Well, you live and learn. So the GitHub was attacked with a memcache attack, but as you can see from the time, it lasted, I don't know, from the time it fully ramped up, maybe 5 minutes. That's unbelievably fast. They intended for it to take them down for days, I'm sure. So why did it take so little time? Because as soon as it happened, GitHub, which is the poster child for mitigation contracts, they had paid Akamai not only to distribute their files for them around the world, so Akamai has servers in every ISP on the planet, and they keep copies of lots of people's files, like all of Microsoft's downloads and Netflix movies, and they are one of the big dominant content delivery networks. And so when you make a request for something, you may think it's really going to Netflix, but it's just going to a local Akamai server instead. And you can find this out by trace routing to those sites, and you'll see the trace route goes to an Akamai Edge server. So one of the things Akamai can do is help you with these distributed denial of service attacks. So when this attack happened, they initiated their policy, hit the alarm button, and immediately DNS updates went out around the world to Akamai servers saying, send all GitHub requests to my local sacrificial server that I put there just specifically to absorb denial of service attacks. Now, that means all users are being sent there. So even legitimate GitHub customers, they're out of business, but they were already out of business, right? So what's happening during this time now is very critical to quickly figure out something about the attack that's unique. The size of the packet, the addresses they're coming from, maybe a bit in one of the fields in the header, maybe some constant checksum value that's wrong, whatever it might be. And as soon as you figure out the pattern, then you push it out to all of these distributed servers around the world that Akamai is running, and they will continue to filter that data and let all the rest through. So GitHub for the legitimate users is back up within 5-10 minutes. And when you read the Wired article and stuff like that, they tell you it's more like 15 minutes or something. But at its peak, these memcache servers were flooding basically a terabit per second and a half at GitHub. No way they have the bandwidth to handle. That's a profound attack. And either in one of the stupidest moves ever, or as I thought about it as the years gone by, maybe one of the most brilliant moves ever, because as I think about it, I think like it couldn't have been stupid. It had to have been brilliant. The manager for this service at Akamai said, wow, the next day said it's a good thing it wasn't 1.4 terabits per second because they would have got us then because that's all we had capacity for. And I'm like, what do you think the next attack's going to be? Genius. 1.4. And I thought, he's not that stupid. It's impossible. He was basically, it's probably something like 50 terabits. He's just going to waste their time doing attack after attack after attack that does absolutely nothing. And in the event, and during the interim, he's going to expose lots of people who need to reconfigure their web servers and things like that and improve security of the network as a result. So take a little bit of fear kind of helps people get this stuff done. So a few other pictures in here on kind of what's going on. Sadly, governments are massive major players in this attack business. No one more than China. And depending on what you want to believe, there are some articles that say China's completely lost control of the situation and it's just rampant within the country as well. And they've got so many people that do attacks, you play with fire, you get burned kind of thing. Who knows? I certainly have no clue about it. But we are not angels either. We make it onto this list as well. And I wonder what the list looks like these days. Let's see if it's got a... So one of the best places to learn about this stuff is from these sites that offer these resources for you. And let me see here, topics, DDoS mitigation. So what usually happens in these websites and these companies that do it, first of all, they write really, really good blogs, and they give lots of details about what's really going on. But I think I've managed to get myself, because I went at this from a weird direction, I may have gone this, okay, now it's secure. I may have gone about this wrong. So live DDoS attack, how to mitigate the threat. Usually within a few seconds, on a lot of these, depending on the page I'm on, something will pop up that says, are you being attacked now? Do you need help? We're standing by. Click here and we'll call you. And because that's usually when a lot of people bother to think about it, is when they're in the middle of an attack. So lots and lots of good information in here on how to educate yourself on what's going on. I just managed to get myself down a 2017 rat hole. This stuff is usually more current than that. Okay, I mentioned that one of the things on here were ransomware as a service. So there were a series of companies, and I'm sure some still exist, whose deal was basically, are you buying gear and implementing policies to help protect your company in the event of a distributed denial of service attack? ? Would you like to know how protected you actually are? We will attack you for a fee, and you can test how resilient your systems really are and have some idea if you're going to be able to withstand one. Or, and so you can pay these guys with Visa, with PayPal, I mean, legitimate money, even $23.99, and they'll attack you for 2,400 seconds at 220 gigabits per second. Anybody here have a line bigger than that? If you don't, you're going down with this attack. So you could pay someone to attack you. It reminds me of the scene in Dirty Harry where the bad guy pays someone to beat him up so he can blame it on Clint Eastwood. So what everybody really does here, though, is they don't go beat themselves up. You pay $23.99 to beat the crap out of somebody you don't like and bring them down. So this went on for a while. So they had this thin veneer of legitimacy, but it was actually organized crime. And there were two really famous sites that were brought down right in the middle of one of my talks, best I can figure out. One of them was Backpage, and they were selling drugs and all kinds of illegal stuff. But the other one that I grabbed was one of these companies called webstressor.org. And I will bet you, and of course this turns out to be like a poster for every logo for every big international police force on earth, because everybody wants to get their hands into it. So they shut these guys down, and everybody went to jail basically. But I wonder if Brewster Kahle, my old friend, Wayback Machine. You guys know about the Wayback Machine? So it's a kid's cartoon from the 60s, but let me see if I can find. It's also known as the Internet Archive, and they keep copies of web pages back for decades. So you can type in the URL and see what it looked like in time. I think I misspelled it probably. Maybe not. Yeah, okay. So the last time they captured it was, okay, so it came up in 2017. So I can go here, and they got a copy of it on June the 22nd. So if I want to see what that page looked like on June the 22nd, I click on it, and here's what their site looked like. So here's what they do. I mean, it looks like a legitimate site, right? Launch an attack, sent successfully for 6,000 seconds, port 80. Web stressor is the best, customer needs, pricing table. So, you could pay these guys and hack sites. Yeah, well, that's one sign right there that you're probably, so if we, and they have fake names and all this, so, I mean, come on. So, these guys are in jail, I assume now. And, okay, so that's an interesting chapter in distributed denial of service attacks. It's insane what some of these guys do. But most attacks last less than 30 minutes. One of the things that Encapsula produced were these wheels that showed for each quarter kind of what the distribution of attacks look like. And about as many people had attacks that were about as many people had 10 plus attacks as had one attack and has had 2.5 attacks. But one poor bastard, the only one who was willing to give him the data, had 242 attacks that month. So this would be like going to breakfast, driving through McDonald's, and they ask you, okay, I would like an Egg McMuffin, would you like an attack with that? Yes, I would. Okay, we've launched an attack. You go back for lunch, would you like fries, an attack with that? Yes, I would like an attack. Every day of the month, you can have 2 or 3 attacks with every single meal you have. How would you like to have that job as that security guy? You just know that every single time you take a drink, buy a Coke, go to the store, whatever it is you do with that periodicity, you're going to be attacked. So I assume it's a big company or a government, but they're persistent, and we got to get a lot better at dealing with this stuff. So far, what we seem to be able to do is just attack them back. I'm not really sure. That's so very militaristic. I'm not really sure that is effective. When I worked at AT&T, one of the things we could see was we knew when new worms and viruses were being launched. We couldn't tell you what they were, where they were from, where they were going to go, but we had such good heuristics that we built up over years for what the profile of data looked like between various backbone parts of the network, that we knew that on a non-Asian holiday Monday at 6 a.m. Greenwich Mean Time, you should see about this amount of data to Europe distributed over these port numbers with these packet sizes and this amount of encryption. So you could build heuristics, big data study on it. It was an early big data study. And then if it varied at all, you knew there was an attack going on. That's how you knew. You would see an uplift in a certain port number, like, well, that shouldn't be happening. 2% more data on this. The volume was so huge that anything that could move the needle had to be an attack. So we could say, like, there's an attack, there's a new virus, and so they would alert people, but that's where the story begins. You have to track it down, and it might take days or weeks before people really become aware of what's going on. Okay, so here's an example of one, and we'll wrap up here soon, but here's an example of one where, and I think this was Neiman Marcus, they had an attack, and they had the right gear, but the volume of the attack was too much for their firewall, and so their firewall was collapsing under the number of TCP connections. If they could just get the data to their intrusion detection system, which is the next red ball looking device here, then it could handle it. It had plenty of bandwidth to grab the bad packets, filter them out, and continue to let the good data go through. So the attack wasn't big enough to fill their internet pipe. It wasn't big enough to bring down their security device, but it did bring down their firewall. But this is an example of where they bought and done all the right things. They just didn't have the equipment in the right order. So in the attack, they figured out they needed to move, with the help of people, move the intrusion detection device outside the firewall, which they might not normally do. And when they did it, they went from 200,000 connections down to a very reasonable level, and it kept their firewall from collapsing, and it allowed their network to continue operating normally. So the attack was unsuccessful as soon as they made that move. So today, when you go into business, when you leave the university and get a job someplace, if you try to manage security on your own, you will fail, and you might want to keep a plan B for a job in your back pocket. The only way to survive these days is with herd protection. And to give you an example, one of the things that Cisco claims is they stop 40 billion attacks a day by using a subscription-based information sharing model, where if one person's subscribed firewall type device starts to get attacked, the security knock at, in this case, Cisco, will figure out what the fingerprint of it is and push it out to all the other customers' subscribed devices. And so they will not suffer the same attack, or if they are suffering, it'll stop. It's the only prayer you have, is to figure out what's going on, have lots of sites out there that can grab things. Once in a while you might get attacked, but most of the time all you're going to be is inoculated. Constantly throughout the day, thousands of new rules every single day being added to recognize and stop attacks. If it gets to the point where it's an emergency response team, then that's like the Akamai specialist or the Imperva and people like that. The remediators is really more like Akamai, large providers who can absorb the blow. So that's a decent strategy for now for how to protect your infrastructure from these types of attacks. But it's a game. We get better, they get better. We get better, they get better. There are some people who've had enough that some of the super skilled ones are now reversing the attacks. And so there's some cool YouTube videos about how people take over the scammer's computer and basically put ransomware on it. And they go berserk on the phone call. So they record the whole thing. And they're interesting. They're usually long, 20, 30 minutes. And they're playing dumb the whole time. But what they're doing the whole time, as soon as they get the connection open, they're hacking into their systems and encrypting their drives. And so that's encouraging to see that. But that's just a game. They'll get better at the other side of it as well. So that's the fun topic. It's kind of depressing, I suppose, now that I look at it. I probably should have had something on the puppy adoption or something, but we had this. That's kind of a distributed denial of service attack as well, though, isn't it? Having puppies, they chew everything up. So we'll have our exam. I'll give you guys a study guide and some stuff to practice. Do you have questions on the homework? Anybody have things that was bugging them that I could make sure that I go over in the review extra carefully? Any particular things stand out? Was the whole thing just a pain in the butt? Okay, let's go over something on Slash, because I got a question from a few people on that. The concept. Okay? So every address can be written as 32 bits. We have lots of different ways of dividing it up. One way we divide it up is by breaking them up into 4 groups of 8 bits each and converting them into decimal numbers. And so you get things like 128.249.27.17, which is the IP address of the first server I ever worked on in 1981. And don't ask me why I remember it. I also remember the first corporate credit card I was ever issued by an employer, 378719609781006. That was an American Express card. I would rather have more useful stuff in my brain I have no control over it. That's what it remembers. So this is just another way of writing down 32 bits. That's all it is. So for every IP address, in order for you to figure out where to send it, you got to know which part of this is the important part of the address that's telling me where it should be sent, and the rest of it is unimportant to me. So think about the telephone network. All the world's telephone numbers. When I am in France and I'm trying to make a phone call to the United States, it's going to be an 11-digit phone number, maybe 13, 14 digits, depending on France's rules about it. But how many digits are really the important ones to know that it needs to be sent across the ocean to the United States? Which two? Just one digit, right? The 1. All U.S. phone numbers from around the world. Our country code is 1. Mexico's 52. France 34. Canada uses the same numbering plan we do. They have the +1 also. We share the same number addressing block. We subnet it between us. Okay, so now that I'm in the United States and in New York City, where France Telecom's big overseas trunk terminates, now there's a AT&T switch, and it needs to figure out to which part of North America this call needs to be sent next. How many digits are important to look at? 3, the next 3, the ones right after the 1, correct? Not 3 at the end or 3 in the middle, but the next 3. And those we call what? The area code. And that'll get you to a certain region. Let's say it's the area code, I can't remember the one for, let's pick 918 for Tulsa, Oklahoma. It goes to a central office switch in downtown Tulsa, and that device then needs to figure out to which of the neighborhood telephone company switches around the Tulsa 918 area code the call needs to go to next. They'll look at the next 3 numbers after that. So at every layer, you look at increasingly more digits, but always starting at the first one up to continuously up to a certain point, and then you stop and you don't care about any of the ones after that. So on the internet, the number of bits that you need to look at are called the network bits, and those are the ones that you need to match to a route in your table so you can figure out is the best way to reach the network that has all of the addresses that start with these bits this way, or this way. Which port do I need to send them out of? Right, so the way you'll use it, the way I tell you how many numbers you need to look at, you guys knew the answer for area code and country code. You probably didn't know the next 3 numbers. I gave you that one, but you can't know on the internet. So I have to tell you how many it is. This is the number of network bits. So you just count up that many bits and you draw a line and you make everything else zeros after it. You leave all these bits alone. You leave them just like they are, and then you convert it back into 8 groups of 8 bits apiece. 8, 8, 8, 8. And you notice the dividing line might fall in the middle of one of these groups of 8. There's no rule that says it falls right here and right here. And country codes aren't all 1 digit long, by the way. We get number 1. Nobody else has a country code that starts with 1. How could they? Some people have country codes that start with 2, and those are 2 digits long. And some people have a country code that starts with 7, those are 3 digits long. So there's a hierarchy for doing it, but for internet network numbers, this dividing line might be in the middle. So if this 8 bits just happen to be 101101000, and there's 8 bits here and 8 bits here and 8 bits here, and I tell you that the end number is 11, where is the 11th bit? In this group, this group, this group, or this one? It's in the second group right here, right? So I'm going to bust this back out to binary if it's in decimal, and I will count up to the 11th bit. Let's say this is 127, and I'm going to cheat by using my calculator because it has a binary mode. And I'm going to do 10110100. 10110100. So that's 180. And let's say this is 37 126. All right? So I get an IP address handed to me. It has this destination IP address. The first thing I need to do before I can find it in my routing table is to convert it to a network number. So I'm going to have to just eliminate the ones that I don't care about. And let's say I've been told that that will be up to bit 11 and everything after that I ignore. So I will count up to bit number 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 right here. And the rest of them I will zero out. 12 through 32 get turned into zeros. So what does that mean? Well, it's easy. This one stays 127. Oops. Doing some avant-garde art here. Avant-garde. This stays 0. This will turn to 0 because all 8 bits got converted. I don't have to recalculate that. This one's going to be harder. This one's going to change to 1, 0, 1, 0, 0, 0, 0, 0. That is a different number than 180. So I'm going to have to go to my calculator and zero out everything after that, and it turns the number into 160. So my network address for this network that includes this IP address I've been given, I now know to be 127.160.0.0/11. You must tell me the network mask, okay? And because the 11th bit falls into this second one, if I want, I can, drop the ones that don't play a part in this at all and just make this 127.160/11. That's okay. You can do that. You can get away with it. Does that make sense? All right, so that's the section on network numbers the book's trying to talk to you guys about. Okay, anything else? Somebody had one on chat. So let me go look at chat. What are the legality issues of these DDoS attacks? Well, it's really a good question. The laws have been behind. So you've got to have laws to make it a crime before you can go after someone for it. So you can try to sue someone civilly for impacting your business, but you can't put somebody in jail for a civil offense. You can try and sue them. Good luck finding them and catching them. Good luck getting the money, right? So it's better if it's a criminal offense, and then you can put them in jail instead. So we are behind on those things. NAT tables are also a big attack vector. I'm not sure if that's where Thomas is going with that because I was very late in looking at the... oh, got it. NAT tables. Okay, got it. What was the answer to how NAT handles multiple clients? Oh, all right, I can show you that one. Yeah, that was a good question. Okay, so let's say you have a NAT router here, and I have one address. I'm going to make it the address 16.20 because I'm getting tired of writing big long IP addresses. Okay, and I have an internal network here, and it has two computers, 10.1 and 10.2. Now, normally when you are connecting to something out on the internet, like a Microsoft server over here, which has the address 3.27, as everyone knows, then you are going to run a client over here and connect to a server over here. And your client will pass through the NAT server, and its source address will be this, and the port number will be random. For most client applications, your client software will randomly be assigned what's known as an ephemeral port number. And you can see this when you look at Wireshark. They're all different ones. It doesn't matter. The important port number is the server's port number, port 80 in the case of a web server. So it's been assigned. You must use it. Your software must establish a connection trying at port 80 first. You may not run any other service on port 80 unless you want people to complain at you. So that's kind of the idea. It's obligatory. There are some programs that assign well-known port numbers on both the client and the server. Mobile IP might be one. There's some other ones as well. Okay, so let's walk through when it's just like a browser. What will happen at the NAT server, it's only got this one address, so it's going to keep a table, and the table is going to have new IP address and port number, and the internal secret private IP address and port number. So you're going to show up with 10.2 and port number, let's say it's random, so it'll be 6523, and so it's going to give you the new IP of 16.20, and it'll use whatever port number is available because it's going to substitute one random number for another. So to keep track of things, it's going to start off at 5,000. And the next person that shows up, they're going to use the same IP address. They can't use the same port or you'll get confused. How would you tell them apart if they both have the same IP and port? So because it has to use the same IP address since you only have one, you'll keep these guys separate from each other by giving the next person that shows up a different port number. And so, 3270, and they may show up with different port numbers already and you could just write them down. You could do that, but the code's harder. This is easier code to write. Just start them off at a number and move up from there. So this works great as long as it doesn't matter to the server on the left whether you show up with port 6523 or 5000 or 5001 or 3273. If it doesn't care, then this works great. The problem comes up if you are obliged to use a well-known port number on the client side as well. And let's say we both need to use port number 81 to connect to somebody at port 80. So this is different than this pair. 10.181 is different than 10.281. I have no problem keeping the track of those two. There's something different about them I can uniquely identify. Their IP addresses are different. It gets to the NAT server. What happens at the NAT server? The first guy shows up, this one down here. He tries to change 10.2 to 16.20, and now he can't use 5000. He's obliged to use a specific port number. It's well known. He must use 81. The next guy shows up. He has to use the same IP address because that's the only one we have. Oops. I don't have another port number I can give him because I must give him 81 and someone else is already using it. So I can only sustain one connection with a protocol that uses a well-known port number for the client. So that was the answer, is going to reduce the number of connections you can have. Yeah, well, it's worth like what, 2 points? I mean, something like that, right? Does that make sense? If it's not required that you use a port number, and if you really want to be a jerk and use all of them, how many different port numbers are there? I mean, how long could I make this list? 5000, 5001, 5002, 28, 10,000. How long could I do this? How many different hosts on the right could have connections that I pass through this NAT server? You might want to figure that out. So it has to do with how many port numbers there are. Okay, hopefully I got that. All right, guys, it's been fun. Now I'm obliged to kind of share the last 10 minutes of this with the other class as well, because we did end up helping you with something that will help on the final as well. The final is not comprehensive. It's targeted 75 minutes. I will cut it off after 2 hours. You can make a dinner date at 7 p.m. and you will be on time, minus travel time, because that's when we're going to end it. And so it doesn't go back to the first homeworks. It only goes since the midterm. There is information in the second half of the class that built on what you learned. So we can't pretend like you forgot what an IP address is or something. But I'm not going to go back and ask you questions from the first half again. Okay? Sound good? All right. Any special extenuating circumstances, like you need to switch or whatever, let me know. I'm much more interested in people moving to this one than moving to Tuesday, because everybody tries to gang up on the Tuesday one and we run out of seats typically. So, okay, anything else? Are they out there or not? Let me look. Let's look real quick and make sure. When did I make the homework due that you guys had? If you're 30 minutes late, yeah, you should be fine. I'm not going to make the homework a 2-hour solid homework, but if you can try not to, that's even better. I wouldn't recommend it, I'll put it that way. Okay, let's go look. Homework 4, there's solutions. 3, there's solutions. 5, there's solutions. 6, It was due yesterday. So I need to give people one more day because you can get 25% off a day. A lot of people ask if it's like 5 minutes late or something. I couldn't care less. The TAs aren't going to count points off for that. They, Blackboard's a jerk sometimes. And I had somebody that turned it in 11:59 and it still counted as late. Well, they don't, I think they're like using an abacus or an old water clock or something. Who knows? Who knows? I'm not counting points off for that program, and I'm leaving a lot of adjectives out right now. So we're not doing that. I can barely tolerate that program. It's okay. I mean, it does a lot, but it's got bugs. They never fix them. And some of them I told them about for year after year after year, and I'm like, why didn't you fix it? I've told you what it is. It's been there forever, and, it's just like telling Adobe about bugs. Like, if it still works and you can work around it, they're not going to do it. They don't care. Just drive around the pothole, Okay, anything else? Going once. I think that's right, isn't it? Right before. Yeah, so 5 and 6 are it, and I will give you guys a study guide. If there is some compelling adjunct thing, I don't think there will be, but there may be something that is closely related to one of these that would be easier and helpful to you. Like I may show you a trace route or I may show you a wire chart, but I'll tell you exactly what it's going to be. And usually when I do wire charts on exams, I give you the trace ahead of time. I actually give you the PCAP file and you can look through it and open it and that sometimes can help as well. Okay, we good? Within the next few days, probably Wednesday, because that's the only day. It's a holiday in Mexico, so you'll have like 2 days basically. But I'm going to try to start with the homeworks. The homeworks are the place to do it. All right, that's your guide. I will. My plan is to broadcast one on Wednesday. I'll give you the recording if you can't attend, but I'll try to record one to walk through kind of what it's looking like at that point. The panic for me will set in on Tuesday, basically. So, all right. Thank you guys very, very much. I enjoyed it. I hope you learned a lot and had a good time. The date is this Friday for this section at 5 p.m. in SEC103, the normal classroom. There'll be some. There'll be some in here like one good example would be, which of the following can I assure using public key encryption like we talked about in class? That's a perfect example of something that didn't have a homework, but would be in the review. We talked about it in detail. And, like, can you assure that Alice can't send a message to Bob? Or so, me come up with yes, no, you can check a few of those things just to make sure you grasp the concepts.
But it'll be in the review.
I'll give you the study guide review for it.
Thank you.
Bye.
I'm sorry, Pastor, you sent you a few emails about the final.
This is the one with the form, right? No. Okay. Tell me what yours was.
Abigail Linden, I have a work